I'm going to show you allocation and dispersion effect in an unreplicated factorial example. This is example 6.4, and it is important to know that it's a 2 to the 4 design. This example is about making the window panels of a plane. So we can see in the video that there's some pressure applied, temperature. The data for this experiment are shown in figure 6.6, which is this one. Wrote down the data. Now I'm doing Yates' algorithm, which is going to be the first data plus the second one, then the third one plus the fourth one, then the fifth one plus the sixth, and so on. The next step is the following. You're going to subtract the second one minus the first one. You gotta respect this convention. So is the second one minus the first number. The second one minus the first. It is important to know in Yates' algorithm that you have to do it as many as letters you have. We have A, B, C, D, so we are going to do it 4 times. And then the 107 that it's under the fourth is going to be the grand total. It is important to have it in mind. Calculating the effects, which are to know which data is going to be relevant for the ANOVA table. The effect is calculated. We grab the data that is in the fourth column, this time is 46, over the time of replicates. We have just one replicate, so it's 1 times 0.5, this is a constant, times the design of the experiment. We have a 2 to the 4 experiment, so we're going to put a 2 to the 4. And we do it for all the numbers except for the grand total, which is 107. Now that we have the effects, we do a table and we paste the effects because we're going to graph them. We put place, standard order, and probability. Now we sort the effects from the lowest to the highest value according to its letter as well. And we sort it, okay, because now we're going to calculate the probability next to it. The probability is the place times 0.5 over the amount of data you have. Since you didn't grab 107, now you have 15 data, not 16, 15. This goes, this repeats the 15, and you do it for all the numbers. You grab the data, you graphed it as a dispersion graph. Now you insert a square. After you do the square, you're going to insert a line to see that the data kind of follows a line, and it allows you to see which data is outside the box and outside the line. So that data is going to be significant. In this case, is A and C. You can see it's out of the box and out of the line. In the graph, we saw A and C were significant for location because ANOVA. So we're going to do the ANOVA table, and we need the sum of a square, which is the number from the fourth row squared over the time of replicates 1 times 2 to the 4th, which is our design. It always has to be the number calculated in the fourth column. So the same for C. And we grab the values and we place them on the ANOVA table. Okay, for the ANOVA table, the grand total is going to be the sum of the square of the whole defects minus the grand total square over 16 because we have 16 data. and the error is going to be the total minus the sum of the square of A plus the sum of the square of C. The defect is 1, and then 1, the grand total is 15, and for the error is 15 minus 1 plus 1. For the meaning of a square is going to be the sum of a square over the degree of freedom. And for the f-test is the mean of a square over the mean of a square of the error. And it's the same for both. We need to do the f-test, which is going to be compared with 0.05, comma, 1 is always 1, and the 13, which is the error degree of freedom. We compare the values we got on the f column with the calculated f, and we see that they are significant because they are greater than the 4.6. The next step is to get the linear regression equation, which is going to be the average and then all the significant effects. So for the first one is going to be the grand total, which is 107 over 16 because it's the whole amount of data. And that's for the first one. And then for the second one is going to be for A, we're going to graph the value of the effect. In this case, it's for 5.75 over 2. And the same for C, the effect of C over 2. Now that we got the values, you're going to paste them 16 times, or the amount of data you have. We have 16, so we're going to grab it 16 times. In this column that is next to A, we're going to put its corresponding signs. For this case is A, so we grab the whole column of signs, and we do the same for C. We paste it, and now we're calculating the expected, which is going to be the B0, which is the average, plus the value of A times its sign, plus the value of C times the sign is next to it. And we do it for the 16 times. We do it 60 times. For the observed, we're going to grab the defects, the original data, we paste it, and for the residual, it's going to be observed minus expected. Observed minus expected. What we're doing next is plotting the residuals. For this, we're going to make the next table, which is place, residual, and probability. For place is 16 places because we have 16 data in total. We grab the values of residual, we paste them, and I'm going to delete the probability because we're not putting it yet. And the residual, we sort it from the minor to the biggest one. And now we have it. Now we're going to put the probability, which is the place, times 0.5 or over 2 over 16, which is the amount of data. And now we have the probability. We grab it down, and we plot it. Dispersion plot. We do this graph so we know there's no data out of place. You can see that the dots kind of follow a line. There's no dot out of place. Once we know A and C are significant, we're going to do the next test. We grab the original data and we paste it in a new page, and we put A plus, A minus, C plus, C minus. And we're going to do the average of where the values of the defects, where A is positive. For example, 11, 9, 8. In these lines, in these rows, the sign of A is positive. We do it until the end. Has to be done with the defects, which is the original data we got from the problem. And then again, the average where A is negative, which is the first one, and then the third one, and then the 0.5, 1.5, and so on until we reach the end. And we do the same for C, where C is positive, and then where C is negative. Okay, now remembering from the problem, we know that location or place is to minimize defects. They ask us to minimize defects. So we're going to grab, we're going to grab the value where A is the lowest and C is the lowest because we want to minimize. In this case, A minus has the lowest value, so it's 3.8, and C plus has the biggest value. The smallest value as well. So we would choose A negative and C positive for minimizing defect. The next test we're doing is for dispersion. We put the letters from A to D and then the combinations. For A, the signs are the same we use the last exercise. For B, C, and D. And then for AB is just the multiplication of the signs of A and B, and the same for C and the rest of them. We need the residuals we got in the last exercise because we're doing the variance. In the variance, it is important to read that variance positive selects the residuals where A is positive, and variance negative selects the residual where A is negative. And for each letter applies the same. For example, in variant A, S, we can see that in the second one, which is R5, in the second residual, A is positive. And then we don't select the next one, we select the the fourth one, where A is also positive, and so on. Every place, every residual where A is positive, we're going to select it. Okay, and then for B, the same thing. We can see the first two are negative, but then the other two are positive, and so on. We select the data where B has positive sign. And for the negative, we do the same thing. We can see the first one is negative for A, then the third one, then the fifth one, and so on. And we can see we do the same for AB. For example, the first one is positive, then the two are negative, then the other two are positive. And I already did the whole table because it has to be done by hand, and it takes a long time to do it. For the F is just the logarithm of the variance positive over the variance where the data is negative. Now we grab the data from the F test and we paste it as values. And then we also grab the letters and we sort it from the lowest to the biggest value. Because we're going to graph it so we know which value is significant for dispersion. We do the probability, which is the same as we did before, the place over 2 times the amount of data. We graph it in a dispersion graph, and we know this dot is out of the line. So we know this one is significant. In this case is B. Now we know B is significant. So we're going to do a test to know whether we choose B positive or B negative, and we grab B and then the residuals, and we're going to make a graph of dispersion, and we see the B negative value are less dispersed than the B positive value. We put this circle so we kind of see how dispersed they are. So we're going to recommend to use the B negative because they're less dispersed. And now for our final answer. The shape minimizes variation, so that's why we're choosing the less dispersed, which is B. And we're going to recommend choose A minus and AC for minimizing defects choose B minus for less dispersion, and for D choose whatever is cheaper because it has no significant effect. And we are done with our test.